Hello everyone and welcome back to Exam Ignite YouTube channel. This is 5th semester digital communication subject of subject code BEC503. This is the continuation of the series that we had started, and here we'll be doing the module 2 where we'll be covering the digital modulation techniques. That is, the first part is phase shift keying techniques using the coherent detection. That is generation part, detection part, and error probability of DPSK and QPSK, which is an important question. Next, we'll move on to the M-ary PSK. In that, what is bandwidth efficiency, and we have to calculate the bandwidth of the M-ary PSK signal. This been asked in the last year paper. Then M-ary QAM, then frequency shift keying, that is FSK techniques using the coherent detection, that is BFSK generation, detection and error probability. Then BFSK using the non-coherent detection. Then DPSK, which is an important part in this module 2. These were some of the questions. So here you can observe BPSK. This has been asked in the 3 papers. You will need to draw the transmitter and the receiver block diagram and describe the probability error along with the current BPSK. Next, in the model question paper, this is one problem being asked. Then QPSK. Then similarly, the generation and detection part you have to explain here. And this is a problem related to average power and all. So we'll be concentrating to this module in the part 1 and part 2 videos. Do like, share, and subscribe to Exam Ignite for these type of further videos. So it's been a very helpful for you for having these type of videos. So please do subscribe to the channel. Next, we'll be starting with the coherent detection of binary phase shift keying, or you can say the coherent detection of the binary phase shift keying and the binary phase shift keying, that is BPSK, using the coherent detection. Here, the first part is signal representation. So basically, in a binary PSK signal, that is BPSK system, there's a pair of signals. Let us consider them as S1 of t and S2 of t. They are used to represent the binary symbols 1 and 0 respectively. So firstly, that is defined by how? So S1 of t is defined by this part has S1 of t has square root of 2 EB by TB cos 2 pi FCT. This is our S1 of t, and the S2 of t is just root 2 EB by TB cos of 2 pi FCT plus pi. So here this lies between 0 to TB for every symbol 1, and this is for every symbol 0. So here our TB is the bit duration and EB is the transmission signal energy per bit. So next comes the FC. FC is what? Our carrier signal, which is equal to NC by TB for some fixed value of NC. So now pair of sinusoidal waves that differ only in a relative phase shift of 180 degree in the equation 1 and 2 is referred to as an antipodal signals. Next, signal space diagram of what we have done. We are having 2 equations, right? So it is clear that one of the basic function of unit energy they are. So phi1 of t equation, square root of 2 by TB cos of 2 pi FCT. The transmitted signal, these two, can be expressed in terms of phi1 of t. So we will replace that. So S1 of t is given as square root of EB and phi1 of t, and S2 is square root of EB phi1 of t, where if we multiply it, we get S11 phi1 of t and S22 phi2 of t, S21 phi2 of t and S22 phi2 of t. This is the equation 4 and this is equation 5. So basically in a BPSK signal system, it is characterized by having a signal space of the dimension n is equal to 1. So in the signal constellation of the 2 message points, that is m is equal to 2 if we consider, then we can write TB. We can write Sij is equal to integration of 0 to TB Si of t into phi of j into dt. So this will be our standard equation. So for this, if you put S11, you get this type of equation. On substituting the S1 of t as square root of EB into phi1 of t, you get this equation. And finally, integration, taking the constant out, that is square root of EB, and integration of 0 to TB only for phi1 of t. So that is 1. So we get S11 as square root of EB. Similarly, you need to find out S12 also. Same way, substitute S1 of t, you get as this. Then phi 2 of t is what? It is 0. So S12 is what? 0. Next, S21. So as for S21, same way, S2 of t. For that, you will substitute this, and here minus square root of EB taken as constant out, and our phi 2 1 square is what? 1. So 1 square is 1, and from the limits and simplification, we get it as S21 as minus square root EB. So next is S22. In S22, same way, S2 of t, it is written as like this, then it is multiplied, so it is 0. So S22 is 0. So signal space diagram for the what BPSK we have drawn here is, now as this is the point of origin. So this is the decision boundary that we are considering. So this is the region of Z1 and this is the region of Z2 for phi 1. So here the decision rule, what is that? It may be applied by setting up an appropriate decisions region as this decision boundary is decided by taking an average between the two message points that we are considered. If the received message lies in the region of Z1, then it is considered as 1 and it's decided. If the receiver signal is points in the region of Z2, then it is decided symbol 0. This is how we consider. Now next, coming to the generation of the BPSK, that is block diagram. You need to know the block diagram and its explanation. So this is directly from the writing from the equation of 3 and 5, which we have shown in the above part. So here, firstly, we give a binary data sequence, some sequence as 0, 1, something you will give as binary input. So that is given to polar NRZ level encoder. First thing. So here, what happens is for square root of EB, it is considered as 1. For minus square root of EB, it is considered as 0. Now product modulator says, so here, from here, we are also giving an input like phi 1 is square root of 2 by TB cos 2 pi FCT. So from here, we get the binary PSK signal, that is our S of t. So this is the generation of PSK. Now transmitter consists of two components mainly. We have to explain them. One is NRZ level encoder, which has a symbol 1 for the positive square root of EB and which has a 0 for the negative amplitude level minus square root of EB. Now product modulator is, what does that do? It multiplies the output of that NRZ encoder to the basic function. This is our basic function what we are having. To this, it multiplies and gives the output. Now the detection of the PSK at the receiver, this is what generation and it is sent. Now what happens to make the decision optimum on the receiver X of t in favor of the symbol 1 and 0, the receiver is synchronized with the transmission basis function, that is phi 1 of t. Let us see how. The X of t that had been generated is being received here and that is sent here to here, and here we send a signal of phi 1 of t. After the signal of phi 1 of t, now we have an integrator, that is from 0 to t dt. From this, we get the output as x1. So this is sent to the decision device to choose 1 if the x1 is greater than 0 and choose 0 if that x1 is less than 0. So let's observe the part here. The whole part of this is known as an correlator. So correlator is one which correlates the received X of t signal with the basis function phi 1 of t on a bit by bit basis. Decision device, what it compares the correlated output. It just compares against the 0 threshold, assuming that the binary symbol is 1 and 0 are equiprobable. Now, if it, as I said, if it is exceeded, the decision is in the symbol of favor of 1, and if not, it is in the symbol favor of 0. So this was all about that. Detection. Now, error probability. This is another one important part where we have to know the error probability of error of VTU with coherent detection. Okay, so here, as I said, it is a Z2 part and Z1 part. This is minus square root of EB, square root of EB for phi 1. So to calculate this probability of making an error, the decision region is associated with error symbol 1 or signal S1 of t. It is described as Z1 is what it is for the positive part. So it is 0 is x1 lies between 0 to infinity, this part. Step 1. So here the received signal of x of t will be what? It is x of t is equal to s of t plus W of t. What is W of t? It is the additive white Gaussian noise. We had learned about this in the module 1 itself. So here next S of t is what? It is a transmitted signal from the transmitter. So for the BPSK, what happens is S of t is given as square root of EB phi 1 of t for symbol 1 and minus square root of EB phi 1 of t for the symbol 0. This lies between 0 to t. Now what happens? X1 of t it can be what we have written here as S1 of t plus phi of omega t. So this becomes square root of EB plus omega t for the symbol 1. Substitution, that's it. And S2 of t it becomes minus it. Step 2 is what white Gaussian noise. Noise means the mean and the variance is 0 and n by 2 respectively. Mean will be 0 and the variance will be n naught by 2. So assuming the symbol is 1 is transmitted, then what will be its mean? Mean is represented by this mu. So mu is given by E of x1. What is E of x1? It is E of that S1 plus E of that white Gaussian noise. So that white noise will be 0, then the answer will be square root of EB. Similarly, variance sigma is equal to variance of the x1, it is variance of this and this. So variance of this is 0. So finally, we get the variance of the Gaussian noises and not by 2. So step 3 is the conditional probability density function of the random variable x1 given that symbol 1 is transmitted. So here all we are doing only for the symbol 1. So what will be that? Probability density is represented as fx of x1 by 1. Then it is 1 by square root of 2 pi sigma. Expression of minus x1 minus mu divided by 2 sigma. Here it is square. Numerator square. On simplifying this, what is sigma value? Substitute the sigma value and substitute the mu value. You get this, and cancelling and simplifying the expression, you get this expression. Finally, here you have to take the squaring on both squaring numerator and denominator, and then finally simplifying, we get this expression. The conditional probability of the receiver deciding in the favor of symbol 0 is given that symbol 1 was transmitted. Therefore, what will be that? P probability, conditional probability, P of 1. It is given as what? Minus infinity to 0, fx1 of x1 by 1 dx. So this is taken and substituted now with the limits. On simplifying that with the limits and differentiating that with respect to considering, and then we have to do some simplification here. And finally, we will get PE of 1 as 1 by 2 Q of square root of 2E by N naught. So here for PE naught, what will be the conditional probability of the receiver? It is in the favor of symbol 1. So given that if symbol 0 is transmitted, then we get the answer as this. Step 5 is, so we need to calculate the total probability for the 0 as well as for the 1. So on adding both of them, we get our total average probability error for the BPSK. So thus the average probability of the symbol error or equivalently BER for the BPSK coherent detection, assuming it is equiprobable symbols, is given by these two equations. So this much you have to write. It will be for around 8 to 10 marks derivation from the detection to the generation and error probability. All these things you will have to write for this answer. Next, moving on to the same way, we need to move for the quadrature phase shift keying. So what this is also one of the type of bandwidth consuming scheme. Here, the phase of the carrier takes the 4 equally spaced values, such as you can consider as pi by 4 or 3 pi by 4, 5 pi by 4, 7 pi by 4, like that. Now the transmitted signal S of t, how it is defined as S of t as square root of EB by TB cos of 2 pi CT plus 2i minus 1 pi by 4 0 to t. It lies between if it is 0 else. So this EP, it is a transmitted signal energy per second. Next, what is TB then? It is a symbol duration. Each possible value of the phase corresponds to the unique debit. So for example, we choose a set of values and represent the gray code and natural code. So example, we'll consider SI of t as S1 to 3. So as I1 and SI2, this will be positive, negative, 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 positive, and positive, positive. So for the negative, it is 0. and for the positive it is 1. So phase for gray code, just write as pi by 4, 3 by 4, pi by 4, 7 pi by 4. Or for this, for the natural code, it will be pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi. Reverse of that gray code. Next comes the signal space diagram for this. So expanding the equation 1, what we had, we get it as SI of t has this. So cos of A plus P is equal to this expression. So using this formula, we open this expression. So we get the in-phase components as well as the quadrature components. So this will be our equation 2. So based on this, we make two observations. One is there are two orthogonal basis functions defined by a pair of quadrature carriers. One is phi1 of t and another is phi2 of t. Same way as we did for the BPSK. And the coordinates of the message will be SI of SI. It is given by one sine cos function, another one is a sine function. The elements of the signal vector like SI1 and SI2, these values are summarized in the below table. So thus you can say QPSK is a two-dimensional constellation with n is equal to 2 and 4 message points, that is m is equal to 4. So the signal space diagram is shown below like this. So here you can observe S1 of t, S2 of t, S3 of t, with S1 of t having the values of 1, 0, S2 of t as 0, 0, S3 of t as 0, 1, and S4 of t as 1. This will be our region Z1, Z2, Z3, and Z with the coordinates phi1 and phi2. So this we'll be joining these dots to get the constellation diagram. So based on that, S1 of t as we have written in the table, write down these expressions. Next, QPSK waveform. This is a question that had been asked in one of the question paper. The input binary sequence is given as this. It is shown in the figure. So this sequence is divided into two other sequences, that is consisting of odd and even numbered bits of input signal. Now the individual PSK waveforms are plotted for both of the odd and the even sequences. Considering the input that had been given, we will be dividing it into two parts. One is 0, 1, 1, 0, and then the 1, 0, 0, 0. So odd bits are given as 0, 1, 1, 0. So 0, we will start from the below, and here it occurs a phase shift. And then for the 1, it continues same. And then again in the 1, it continues the same. And again for the 0, there is a phase shift. Next comes the even bit. In the even bit, you can observe same way. 1 starts with the upper one and then upper part, and then we go here. Again for the 0, there is only one phase shift here, and for the 0, it continues the same. Only when the bit changes, there is a phase shift. So for the 1, 0, it is 45 degree. For 0, 0, it's 135 degree. For 0, 1, it is 225. And for the 1, 1, it is 135. So we will write the QPSK waveform based on those two BPSK. So this is how here it, as I said, 45, 135. This one is 225. This is 315. Next is the generation and detection of QPSK. So here the block diagram for this transmitter and the QPSK receiver is shown here. So firstly, we provide the binary sequence data as usual as 1, 0, 1, 1, something we provide. Then polar NRZ level encoder is there. Then here we have a demultiplexer. Again, it is divided into two parts where we will be providing an input for cosine function as well as a sine function. Finally, we will again sum it up and give out the QPSK signal, that is S of t. This is our QPSK transmitter. In the receiver part, what happens is this X of t QPSK, what we had got, that is sent. Again, we are having two parts, that is phi1 of t we are providing and then phi2 of t. Again, we are having a integration part here, integrator, to provide the x1 and x2. In the decision making, if the threshold 0, it is estimated as 1 or 0 and then sent to the multiplexer. This estimates the binary sequence and gives us back the QPSK receiver. So in the transmitter, as I said, we are having a demultiplexer. In this, where the QPSK transmitter divides the binary wave provided by the NRZ level into two separate waveforms, one which represents the odd number bits and the incoming binary sequence, and the other represents the even. It may be viewed as two binary PSK generator that work in parallel. You can note down this. It works in parallel, each at the bit rate equal to 1/2 of the original binary sequence at the input. Next comes QPSK receiver. In this again we are having two paths, where the upper path is known as the in-phase path and the lower path is known as the quadrature path. So these are also worked in parallel. So this consists of composition of QPSKs as follows. One is pair of correlators which have a common input, that is x of t, and two correlators are supplied with a pair of locally orthonormal basis functions, that is phi1 of t and phi2 of t, as I said. So here it is synchronized with the transmitter, and this correlator outputs are produced in response to the received x of t and are denoted as x1 of t and x2 of t respectively. Next comes the decision making. We are having two decision making pair, that is which acts on the correlator outputs. What it compares with a zero threshold. That is 1 and 0 symbols are assumed as we need the original binary sequence and the transmitter input are equally likely. If, as usual, if x is greater than 0, that's in favor of 1 and in phase channel. If x is less than 0, then it is favor of 0 and it is quadrature channel. In multiplexer, what we had used, it is used to combine the two binary sequences that are separately produced by the two decision devices. So this results in a multiplied binary sequence. So that provides an estimate to the original binary stream that had been transmitted at the input. Next is error probability of QPSK. So again, as usual, we will add an white Gaussian noise for x of t received signal. That is given as xi is equal to s4i plus omega, assuming we are having 4 is the transmitted signal where I is equal to 1, 2. So what will be the signal? We are having x1 and x2 square root of e by 2 plus omega. So we need to find the mean and the variance. Mean will be 2 and the variance square is n naught by 2. Conditional probability you need to find with the same formula for x1 by s4. So on simplifying as same as we had done in the BPSK, same thing you need to do. When the signal of s4 is transmitted, the receiver part lies in the region 4. So if x1 is greater than 0 and x2 is greater than 0, this is leading to the correct decision. That's the probability of what the correct decision PC of S4 of t when the signal is S4 is given by this expression. Since we are using a random variables, they are statistically independent to the joint probability to the product of equivalent individual. We can write it as separate probabilities, joint probabilities. And substituting the above equation, we did multiplying and dividing by 2. We get this, and then individually separating it out and changing the limits. On substitution, we get a complementary error function ERFC is equal to 1 minus Q square root of E by N naught. After that, again we expand. So finally, we get the average probability symbol error for the QPSK has 2Q of square root of E by N naught. So here you can observe here there are 2 bits per symbol, and hence it is transmitted energy is twice. So you can write E is equal to 2 times the EB. Hence the average power of that will be 2 times Q by Q square root of EB by N naught. So BR for the QPSK will be Q divided Q of 2 EB by N naught. So it is half of that, you can say. Then comes offset QPSK. This is about the shift. So this is not that important. If you want, you can just pause the video and just do refer to that. It is actually easy, not that complicated. Next, we'll move on to the M-ary PSK. This is a form of completely referred to as an M-ary PSK, or you can say MPSK. It is MPSK phase of carrier that takes one possible M value for theta 1 is equal to 2i minus 1 pi by m, for I is 1 to m. So one of the M possible signals that can be represented is Si of t. It is given as square root of e 2e by t cos function, where I is 1 to m. So here what is our E? It is a signal per symbol. So carrier frequency Fc is Nc by t for some fixed integer Nc. So each assay of t may be expanded in the two basis functions, that is phi1 of t and phi2 of t, as like that with a two-dimension constellation diagram. So the M message points equally spaced on the circle of the radius root E at the centered origin. So this is called as opto-phase shift keying. You can say this where here the M is equal to 8. So here In the figure 1, we will show the message points of m is equal to 4. You can consider the m1, m2, m3, m4, and this is our decision boundary for 5. So similarly, 5 and 5 2, this is our decision boundary where we are in m1, m2, m3, m4, m5, m6, and m7, m8. So this is octophase shift keying. M is equal to. So we see that signal space diagram is circularly symmetric. Next comes channel width. This is required to pass the M-ary signal. B is equal to 2 by T, where this had been asked in one of the question paper, and M-ary is a very important topic. It has been asked in the last year question paper. You need to define a bandwidth and then you have to tabulate this bandwidth. So it is required, channel bandwidth is required to pass the M-ary PSK signal. That is given by B is equal to 2 by T, where T is a symbol duration and T is given by TP. Bit rate is what? RP is 1 by TP log 2 M by TP. So this equation 1 can be rewritten as 2 by TB, but TB is substituted with this. So finally we get this as the answer. So here our RP is bit rate and M is given by 2 power n possible values and capital N is given by number of orthogonal basis function. So bandwidth efficiency that had been asked, that is given as RB by P. So RB will get cancelled. It is log 2 of M by 2. So let us consider some bandwidth for values to find out the bandwidth efficiency of M-ary PSK. It is 2, 4, 8, 16, 32, 64. So substituting to this M place and finding out the values, we get the bandwidth as this. So these are the number of states of M-ary PSK is increased. The bandwidth efficiency is improved at the expense of the error performance. So this was all about the M-ary. Next.